Oxford University before moving to Bristol University in 1976. Since 1992, he is a professor of mathematical statistics in Cambridge University. He is a leading figure in random systems, especially percolation theory and contact process. He was awarded the Rollo-Davidson Prize in 1989, and this year he was elected a Fellow of Royal Society. He was also involved in several professional activities. He was associate editor in analytical probability, managing editors in probability survey and probability theory and related field. Currently, he is one of the IMS Council and the editor in Journal of European Mathematical Society. He will talk about criticality, universality, and isoradiality. Let us welcome him with a big hand.
Thank you very much for that kind introduction. I'm going to try and speak without the microphone, but if you can't hear me, then please indicate and I'll go behind the microphone. Let me make it, first of all, completely clear that when I was asked for my biography, that is not the one I provided. I am very relieved to find that I'm a Fellow of the Royal Society, but I have resigned from the board of the Journal of the European Mathematical Society. It's quite all right, thank you, but that's very sweet of you to speak like that. Let me express my deep appreciation to the local organisers for this stupendous and remarkable show, this conference which has been organised for us. It's only, of course, the second day, but I'm confident it's going to carry on in this very glorious way. And I'd like to say also extend beyond the local organisers to not quite all Koreans, but all Koreans that I've met. I arrived in Korea on Friday morning, at least on this trip. I arrived in Korea on Friday morning, and everybody that I've met has been extraordinarily gracious and friendly and helpful in a way which I'm very unused to in a strange country. And to paraphrase, strange doesn't, you understand what I mean. Comme un étranger. And to paraphrase an expression used to me recently by my son, who's traveling in another country, another strange country, he said, you know, the worst example I've had is mere friendliness. So this is a talk about an old friend of probabilists, the percolation model. What the percolation model is, if you don't know, will emerge during the talk, but the percolation model is a model for a random medium that has the minimum amount of dependence, so it's built on tosses of coins. Of course, everything is built on tosses of coins, but this is done very explicitly. And this is a talk about universality, which is a word which is occurring in several talks in this meeting. So universality is a rather generalized concept, but in the concept of this talk, it's really the classic sort of universality of mathematical physics, that there is a singularity, and the nature of the singularity should not depend upon the microscopic structure of the process. So the nature of the singularity should be invariant with respect to a class of models. The universality is a very elusive concept in mathematics. There are very few complex systems for which we have proofs of universality, though there are very strong indications, very strong arguments, particularly out of physics, renormalization being one of the main words here, that indicate that universality is valid. Nevertheless, the search for rigorous proofs is proving difficult. That's the overview of my talk. This is what we might call the big picture. These are the things I'm going to do. I'm going to talk about phase transitions in complete generality. The results of this talk are all to do with 2 dimensions, which is, of course, a rather special number. Well, it's more than 1. I'm going to define the percolation model, and I'm going to talk about universality of percolation models in 2 dimensions. I'm not going to describe the proofs, but I assert there are proofs. And if I've got time, I'm going to present some open problems which I personally find fascinating. So the general concept of phase transition is that you have some system. Typically, it's going to live on a lattice, a square lattice in 2 dimensions, or a cubic lattice in a higher number of dimensions, or some graphical structure which has some rich automorphism group in a certain dimension of Rd, embedded in Rd. So this number d up here is quite important. There's a system going on, it's a stochastic process, and there's a parameter. Let's just take one parameter, and that parameter could be temperature, could be density or fugacity. It's some continuously varying parameter. And what we prove first is that there is a value of that parameter at which something critical takes place, at which there is a singularity. There's not always, of course, a single singularity. There are models for which there's a multiplicity of singularities, but the mathematically most tractable situations arise where there's a single singularity. And here's a picture of what can occur, and those of course, those of you who know percolation know what this picture comes from, but essentially you have a parameter p here. This is sort of generalized pictures of parameter p, and there's something that you calculate based upon the infinite volume process, and you plot this, and there is a point at which it is singular. And that point would be the critical value of the parameter, the critical value of p in this case. And the two obvious questions that you would ask are, what is PC? That's the question of criticality. Where does the critical point occur? Where does the singularity occur? And secondly, here is a singularity. What is the nature of that singularity? How do you describe it? In what sort of class of singularity should it lie? So the concept of universality will say that the value of the critical point is very, very model specific. If you change the graph a little bit, you get a different critical point. But that the nature of the singularity should be robust within a family of models of similar type. For example, a family of models of the same dimension. So that the three basic areas in which one seeks answers are: the critical point here separates a subcritical regime from a supercritical regime, or two different phases. What are the structures of these phases? What can you say about the stochastic system in these separate phases? And what happens at or near the singularity? And in particular, can you, from understanding what happens at and near the singularity, can you extract statements such as scaling theory? Scaling theory is about the nature of the singularity. There are exponents, these are power law singularities. Can you calculate the critical exponents? And in particular, can you show that they're universal across a family of models? So this is only about 2 dimensions. We know an awful lot about 2 dimensions, but there's an awful lot that we don't know. We know very, very little about these systems in 3 dimensions, and then as the number of dimensions increases, our knowledge increases for reasons which are nothing to do with the content of this talk. So in 2 dimensions, what is special is that the goat is in a field, and the goat walks along paths which are 1-dimensional, but the goat is constrained to a field by a fence, and the fence is also 1-dimensional. So it's to do with the fact that the codimension of 1 dimension in 2 dimensions is 1. So it's to do with the fact that down here, this little equation, which we teach our children, I mean, in a sense it's a definition as much as an equation, but this trivial little equation actually gives rise to a substantial number of structures in interacting particle systems. And when you perturb this equation in some way by changing the process which leads to one of these 2 numbers on the left-hand side, life becomes very much more complicated. So 2 reasons why 2 dimensions is special is: one is because boundaries are 1-dimensional, it's a topological statement. And the other one, of course, is because 2 dimensions is also the Argand diagram, it's the complex plane. And so it comes with a complex structure, it comes with analytic functions and all that goes with analytic functions. So what's universality? So as a hypothesis, this states that the microstructure of the model does not affect the nature of the singularity. The microstructure of the model. So what would microstructure mean? So you take a certain type of model, such as percolation, which is forthcoming, then you define that on a graph. The graph lives, for example, in 2 dimensions. It could be the square lattice, it could be the triangular lattice. They'll have different critical points, but the natures of the singularity should be the same. The same in the sense that they're given by equal power law. Power law behavior. Those objects which are singular have power law behavior, and the exponents should be constant. So the nature of the singularity should be invariant with respect to the microstructure. This is a very elusive concept for mathematicians. The usual argument that one encounters from those trained in physics is that the route to proof of universality lies through renormalization. And renormalization, real-space renormalization has attracted a great deal of attention, rightly so, and in a number of situations, in some sense, it gives you the right answer. There is a view that in order to prove universality, we therefore should prove a renormalization. This has proved extremely difficult to do, and it could well be the case that in order to understand universality, actually we need to construct a parallel route, a route parallel to renormalization, which in a sense explains renormalization rather than renormalization explaining universality. We don't know. There are a few rigorous applications of, I mean, the emphasis here is upon rigor. There are very few rigorous applications of renormalization in this sort of context, but they do exist, but they are very rare. Now, what models might one apply this general worldview to? And the answer is there's a whole wealth, collection of really exciting models that live between mathematics and physics. And it's an enormous project of mathematics and mathematical physics to understand the nature of the critical points, the nature of the singularities in these models. And this massive project is ongoing. It's ongoing around the world, and tremendous progress is being made. But it's very massive, and there's a very great deal to be done. So as I say, in 2 dimensions, we can do a great deal. 3 dimensions, we can do relatively very little indeed. And there are a number of objects in 2 dimensions which play a role here. The objects which do not feature in this lecture are, for example, SLE and the Gaussian free field. So let me move straight on and talk about what percolation is. So percolation is a model for a random medium introduced in the mid-50s by Broadbent in a paper, by Hammersley in a paper of Broadbent and Hammersley. So this is the bond model. So these bonds or edges are going to support random variables. They're going to support coin tosses. So you look at a particular bond, let's say this bond here, and you flip a coin. And if it comes up heads, you keep it. If it comes up tails, you throw it away. So I threw it away, it came up tails. Now I throw the same coin for all the other bonds, and I keep them or I throw them away. So I throw, and this is the same coin, so it comes up heads with probability p every time. The same p occurs every time in this particular model. Later on, we're going to see inhomogeneous models. So we see, when we've done that, we see a subgraph of the original graph. And thinking about this as a model for the transmission of water, imagine we push water in at the origin, and water goes down these pipes which are present, and it reaches exactly what we call the open cluster at the origin. So if we supply water at the origin, it flows down the edges which are retained. It's blocked by the edges which are deleted, of course they're no longer there. And we ask the question, as p varies, is there a singularity? And so the object that we study is this guy here. This is the probability, there's a little p there to remind you that there's a parameter here which we're going to vary. It's the probability that the origin is connected to infinity in this red graph. So it's the probability that if we supply water at the origin, then it wets an infinite set of vertices. And if p is very small, such as 0, it's clear that all edges are deleted, so this must be 0. If p is larger, such as 1, then all edges are present, and so it's 1. So it's got to get from 0 to 1, and it can't go down, because increasing p means more edges. So it's got to get from here to here without going downwards, or without going strictly downwards. So in general, what it might do is it crawls along the axis for a time, and then it diverges from the axis and heads up to 1. So this is, in a sense, a theorem. This picture is a theorem. You have to be careful about the theorem, which in a way that I'll describe in a moment, but this is the sort of canonical picture for what's called the percolation probability. So the canonical picture is that it stays on the axis to some PC, and that is exactly the singularity. At PC, it moves off the axis. That's perfectly clear, because theta is a monotone function, so there must be such a PC. That PC is non-trivial, you don't have to prove that. And afterwards, well, I've drawn an apparently smooth, well, I don't know how XFIG computes its picture, draws its picture, I don't know how smooth this is, but it looks smooth, it looks concave, it looks continuous at PC, so there are a number of questions about that. Just to indicate the next open problem for percolation, we know, well, here are 2. One of them is a little bit of a mathematician's problem. We have a general proof in any number of dimensions that this function is C infinity. Infinitely differential. We have no proof that it's real analytically, at least a curiosity. You can do it in 2 dimensions, because 2 dimensions have got special properties, but we have no proof in 3 dimensions. Curiosity. But actually the open problem is whether in fact this red curve descends continuously to 0 at PC or not. I just mentioned that. So this is that we have the critical point here. There's the critical point. The question is it true that theta of PC is 0 for all lattices? Let's not go into what a lattice is, but you can see what I mean by that. So this conjecture, I was just asked in the 2 minutes before the talk began, actually. Suraf came up to me and said, by the way, have you got any idea how to do theta of PC equals 0? Because he has, but never mind, we'll talk about that afterwards. To which I say a lot of people have had ideas how to prove theta of PC equals 0. This question has been around a long time. It's been, in a sense, the next question to solve since about 1985. I mean, it existed before 1985, I assure you. The world hasn't changed, but it emerged in the mid-80s as the next problem to solve. So I suppose it still is the next problem to solve. Now, in 2 dimensions, a lot of special things occur. First of all, the critical point is a half. Okay, I mean 2 dimensions on Z2. That's because of duality. The dual of the square lattice is the square lattice. So if you know what I mean, then you see what I mean by that. But turning it into a proof is complicated. And we also have, in 2 dimensions, there's no easy way of getting away from the origin in 2 dimensions. In 3 dimensions, you could play a lot of games, and it's much harder to control these things. But in 2 dimensions, we know that at a half, there is no percolation. But I just want to underline this, if you want to, don't give it to your PhD students, but if you want to think about it on the way home. Now, why are we interested in percolation? So a variety of reasons are present on that overhead, and I'm not that transparency, and I'm not going to read them out. One reason I think, you can argue it's a very interesting model, it's related to physics, it's a playground for developing new techniques which are arguably and often are useful somewhere else. Or another one is if you take a complex physical model, you often can't understand very much about it, but when the parameter is very small or the parameter is very big, you can do comparisons with an easier system. The easier system can be percolation, and so percolation gives you methods of understanding high temperature and low temperature behavior of more complicated systems. The difficulty then is to get the high temperature and the low temperature understanding together at a critical point, and that's often extremely difficult and requires techniques which are very adapted to the process. But comparison, it's useful for comparison. It's also, if we can borrow from Harry Keston's opening paragraph in his preface, mathematicians, probabilists usually regarded as a very beautiful problem, a very simple situation where there are very hard problems which are easy to state, which, as I put it, you can explain to the bus conductor. Now, let's move on to universality. So universality in this universe is going to say that the nature of the singularity does not depend upon the microstructure of the lattice. So what lattices? Well, there are 3 lattices. The square lattice on the left and its dual lattice, which is square. The triangular lattice on the right and its dual lattice, which is the hexagonal or the honeycomb lattice. So there are 3 lattices. So the first conjecture, they've got different critical points. Actually, we can compute the critical points of all those 3 lattices, which is unusual. That's because they have this special duality structure together with, on the right-hand side. This is dual to itself. The red is dual to the black, but the star triangle transformation gives you another way of moving between these 2 lattices, so you have 2 relations. And given all that information, it's possible to compute exactly the critical values of these lattices. But until recently, we had no proof, or no idea of a proof, of showing that the nature of the phase transitions on these 3 lattices are the same. In other words, that the critical exponents, whatever they are, that comes later, the critical exponents on the blue, the red, and the hexagonal lattice are equal. But it turns out that there is a technique which vastly extends the space of models on which we can work from these 3 lattices to a collection of objects which arise through rhombic tilings. Rhombic tilings are truly beautiful and magical objects. Of course, they've been around a long time. It's said that in the Alhambra there's a Penrose tiling behind the bath, to which I say the wall behind the bath is always finite. How do you know it's a Penrose tiling? So that's a bit of the Penrose tiling. Penrose Penrose discovered that he discovered this. Actually, that's not a bit of the Penrose tiling, but it's just a bit of the rhombic tiling that I drew on my computer. But a Penrose tiling then is a tiling of the plane using 2 distinct types of rhombi. So you've got crate 1 containing rhombi of a certain aspect ratio, and you've got crate 2 of another aspect ratio, and you want to tile the wall with tiles of those 2 types in such a way that there is no periodicity, there is no translation, it's not even invariant under no translation or rotation, no non-trivial, you see what I'm saying? And so Penrose proved that it was in fact possible to do this. He proved that by constructing a tiling, by giving rules for constructing such a tiling. De Bruijn, in 3 extremely beautiful papers in the early 80s, pivoted off Penrose's construction to construct a continuum of such tilings, and indeed a vast generalization of the Penrose tilings in an extremely beautiful way in 3 single-author papers which are extremely compelling reading. In fact, all De Bruijn had done, and it's really only a very small amount of what De Bruijn had done, then it would still be enough to gain him extraordinary notoriety as a mathematician. So there is a rhombic tiling. Every face is a rhombus. Now, rhombic tiling is a bipartite growth. because every face has even degree, and every cycle is the union of two of faces of even degree, and therefore every cycle is even. So this is a bipartite graph, and I've coloured the sets of vertices red and white. Now, so from that bipartite graph, we're going to construct a graph, and the graph is going to be derived from the red vertices. I could have used the white set. In fact, I could have used my colours the other way around, but I'm going to use the red set. If I'd used the white set, I'd have got the dual graph. So what I'm going to do is you take a rhombus, and you join the two opposite vertices of the rhombus, which are coloured red. So then you see a red graph. Now you see, if I'd done the white graph instead, that guy would be joined to this guy, would be joined to this guy, and so on would be joined to that guy. I'd have got the dual graph of the red graph. So there's a sort of, yeah, so there's the graph. Now that graph, for that graph we use the word isoradial. Isoradial is a word used by Rick Kenyon. It doesn't annoy me, I like the word very much, but of course it is what we might call a bastard word. You do understand what that means. Maybe in Asia one doesn't look at it quite that way. So, what's the property of an isoradial graph? It has the property that every face possesses a circumcircle, and those circumcircles have equal radius. So isoradial, every face has a circumcircle, iso, equal radius. So an isoradial graph in R2 is a graph with that property. And the proof of that property simply, it's a trivial consequence of the fact that it's come from a rhombic tiling. Whatever rhombic tiling of the plane that you pick, if you construct that red graph or the white graph, you will end up with an isoradial graph. So isoradial graphs are just a family of graphs in R2. And what we notice about them is that whereas the vast majority of arguments in this area of mathematical physics use symmetries of the graph, such as rotation, translation, reflection, the property of isoradiality has nothing whatsoever to do with translation, reflection, rotation. It's isoradiality, it's different. So if we're going to prove something for isoradial graphs, we must be very careful to avoid those pitfalls in proving things when you use somebody's famous proof and you don't notice that on page 33 actually he or she has used reflection in the origin or something in some surreptitious way. Harry Keston was very good at this. Whenever he used symmetries, he was very clear about the symmetries that he used. So his proofs are, in fact, classes of proof for which it's quite easy to uncover exactly the assumptions which he's using. And he brings them to the surface in a very interesting way, a very useful way. So isoradial graphs. Now, De Bruijn showed something else which is really extraordinary. And he showed the construction, he called them ribbons. Rick Kenyon calls them tracks or train tracks, and the other expressions have been used. But this is really the way in which you describe your Penrose tiling or your rhombic tiling. So what you do is the following. Start with an edge. Here's an edge. What I'm going to do is I'm going to cross that edge. When I cross the edge, I decide I'm going to cross the opposite edge. And then the opposite edge, and there's always an opposite edge, and from there the opposite edge is there, and then the opposite edge is there and there. So this track always traverses opposite edges. And I do that for every edge, and I traverse it, and I continue the ribbon in both directions, and I construct this this set of doubly infinite blue lines. And you can think about these blue lines in a variety of ways. You can think about them actually as the union of the rhombi that they cross. You can think about them as a union of line segments which simply join straight line segments between the midpoints. Or you can throw away the original graph entirely and just keep the blue lines and think about that as a graph, just the graph structure, not the embedding into R2, but the graph structure. So here are there is a vertex in the blue graph. There's another vertex, and there are edges between them in this way. So what I'm trying to say is that it's useful in this area to think about the blue lines not only as arising from the rhombic tiling and giving you information about the way the rhombi relate to each other, but also to think about it as modulo homeomorphism, just as a graph in the plane. If you perturb the graph, by perturbing the graph, I mean you perturb the embedding of the graph, it's still the same graph. So it contains information as a graph. It also contains information through the lines of rhombi that a ribbon or a train track crosses. So here are some examples of track systems. Now, this doesn't look like a track system, it looks like a square lattice. But actually, if you start with a square lattice and draw its track system, and then straighten out the tracks, that's what you get. So the square lattice is a lattice which is not only self-dual, its track system is also isomorphic to the original graph. The Penrose tiling discovered by De Bruijn, this has got two sets of parallel lines. The Penrose tiling arises through taking 5 sets of parallel lines, coded by these different colours. In the Penrose tiling, these lines are equidistant. Yellow to yellow is distance 1, say. All the reds are distance 1. Those are numbers which we could vary. They don't have to be the same, but in this particular picture they're the same. And they're at certain angles, so for each colour there's an angle relative to the x-axis. So there's some parameters I can play with here, but if I choose those parameters correctly, I get true Penrose tiling. The one thing you have to be careful of in general is that you're allowed to have two-way intersections here, because tracks they do cross on rhombi, but tracks never have three-way intersections. So you're not allowed combinations of angles and distances which give you three-way intersections. So if you find a three-way intersection, you need to take an entire set of parallel lines and move it slightly in order to avoid that three-way intersection. And then once you have such a picture, you can engineer backwards to find a rhombic tiling of the plane that corresponds to that. We need a little bit more information, because I don't give you everything there, but that together with a bit more information will allow you to construct a rhombic tiling. And so here is just to remind you of the floor on the New Maths Institute in Oxford, which I haven't seen yet, and I think there's also one in Durham. Isn't there? This is a Penrose tiling. That's the actual Penrose tiling. That's the isoradiograph that comes from it. So there's the isoradiograph, here's the proof of isoradiality, and here's the track system. And you see that coloured the sets of tracks which are not parallel to each other quite, but you can move them smoothly in order to make them parallel to each other, which are the track system of the actual Penrose tiling. So this is a particular Penrose tiling, but remember, there's a continuum of tilings of this sort. In fact, in a sense, several continuum of tilings. Now, we need, for our results, 2 properties. So I just state them very quickly. First of all, we need that the rhombi are never too flat. If the rhombi are too flat, then locally odd things can occur. So we need a uniform bound on the rhombi. That's the only assumption on the shape of the rhombi, that no angle of any rhombus is less than epsilon or bigger than pi minus epsilon. And the second property that we need is when we look at the set of tracks. So this set of tracks is just, as I indicated back here, the set of tracks is that set on the right-hand side. If I look at the set of tracks, it's got to contain a square grid in order to make our techniques work. We believe the results are true without that property, but we don't know how to eliminate that property. So of course, the true Penrose thing, it's got a square grid many times. You've got 5 choose 2 square grids, actually. So there are an awful lot. We've got 10 square grids in it. We only need 1. Penrose tiling and things like it are really no problem. In fact, any of the rhombic tilings arising through De Bruijn's menu for constructing them by projection, cutting and projecting, will have this property. So the set of graphs that we're working on is the set of all isoradial graphs with the bounded angles, satisfying the bounded angles condition and with the square grid property. So you can just file it away that there is a condition, but the condition is not too restrictive. Now, why do we care about isoradiality? Well, because it enables us to prove theorems. But what's magic about isoradiality is there are 2 things which are magic, 2 probably related things. One is that it's the right universe for what you might call discrete analytic functions. This was discovered by Duffin. The ideas were around in the late 60s and the 70s, but Duffin, 1968, is the paper that made this very explicit. Duffin was probably the person who first discovered this. So if you want to construct not an analytic function, which is a function on the whole of the complex plane, but something which is living on a discrete subset of the complex plane, so it's a discretized version, then the isoradiographs are the right universe to work in. And Duffin didn't call them isoradial, but he did write down the definition of isoradiality. And the second thing is that it's a good place to use what's called the star triangle transformation, which I'm going to come to later. Star triangle transformation was discovered in 1899 by Clinelli to understand electrical networks. Take a star and a triangle, you can change them such that you have to map the electrical resistances of one onto the electrical resistances of the other, and the network doesn't notice. But the star triangle transformation, which in physics speak is the Yang-Baxter, and the Yang-Baxter, in the sense of Yang-Baxter, it's an enormous extension of the star triangle transformation. But the isoradiality and the isoradiographs are very good places to do star triangle transformations. So let me move on to percolation. So we have an isoradial graph. The square, if you don't like the generality of isoradial graphs, just take the square lattice. Square lattice is isoradial. All this triangular hexagonal, they're all isoradial. They're isoradial with tremendous regularity. In general, that regularity is irrelevant to the arguments. So here is an isoradial graph. Here is a face, a pentagon in the isoradial graph. There's another pentagon, a triangle, and a rectangle, and a quadrilateral. Now these edges, we're going to do a percolation model. So I want to tell you what P is for that edge. It's no good now. Nobody knows how to do constant P for this graph. We have to let P depend upon the edge. That seems to be the right way to do it in some sense, which means that there's a wrong way, which is much harder we don't know how to do. So the P for this edge is a function of this angle of the rhombus. This edge is a diagonal of a rhombus. That rhombus has an angle. So the value of P is going to depend upon the shape of the rhombus according to this formula. Why this formula? Because it works for the star triangle transformation. Might have time to explain that. But so what we're going to do, let me recap. We're looking at an isoradial graph in R2, embedded in R2, with two properties, which I've explained, but we don't have to recall. And on that isoradial graph, I want to do percolation. But I'm going to have to choose it's not just any old percolation, very special percolation, where the probability an edge is present depends upon the shape of the rhombus, of which it is a diagonal, and the value P on that edge is given by this formula. Never mind what the formula is, there is a formula. And so here is a theorem. This is a theorem with Ioan Manolescu, who was a PhD student in Cambridge and is now a postdoc in the University of Geneva. And before he came to Cambridge, he was in France. Before then, he was in Romania. Who knows where he's going to go next? And it says the following. So, first of all, there is a technical property. The key to all this is what's called the box crossing property. This means that it's to do with probabilities of crossing rectangles, being bounded away from 0 and 1 at the magic point. So there is a technical condition called the box crossing property, which I'm not proposing to talk about in this talk. But essentially what we do is we formulate the box crossing property and we show that the measure on G, that's percolation on G, that's the corresponding percolation on the dual of G, that's the white graph. This is on the red graph, this is on the white graph, that they both have the box crossing property. And when you have that box crossing property, you can build off it to prove that these two measures, PG and PG star, are critical measures. So for example, for the square lattice, if we go back to the formula, the value of P is always a half, and so this says that a half, P equals a half, is the critical point of the square lattice. Of course, also triangle and hexagonal, but I emphasize there's no automorphism, no non-trivial automorphism group in these graphs. This is so we're not using any regularity on the graph, we're using isoradiality. And anything which imposes more than isoradiality, in a sense, cheats isoradiality. Furthermore, this set of graphs is a universality class in the sense that, so what's a universality class? It says that the nature of the phase transition, the nature of the singularity, does not depend upon the graph. So when I say G is a universality class, I mean in a certain very specific way that each graph in this family has a transition. The transition takes place, well, this is a measure which describes the critical measure of this process. And at this measure, there is a transition. We encode that transition in terms of what's called critical exponents. And what this says is, at first sight, it says that there's a very large family of critical exponents. We can't really call them, which are the same across this entire family of graphs. So within this very large family of isoradial graphs, this family of exponents is constant. Now there is a little problem, a little flaw with this. The little flaw is that we can't actually prove that any of these critical exponents exist for this family of graphs. So maybe this is the next but one question. Well, actually it's been the next but one question, I guess, since Stas's proof of Carly's formula around 1990. Try and do something non-trivial for any one of these graphs. We can't. We don't know how to do it. We don't know how to prove these critical exponents exist. There are upper and lower bounds, so we know that they can't be too big and they can't be too small, but we can't prove that the limits exist which would enable these exponents to be defined. Actually, the only exponents we can deal with for experts are those exponents at the critical point. We can't move away from the critical point. We don't know how to do that. We could move away from the critical point if we added a little bit of regularity to the graph. I don't want to, and then it becomes easy to see how we do that because there are results of Harry-Peston which are just ready to be used in this context. But one doesn't want to do that because then you're using substantially more than the isoradiality which you're allowing yourself. So let me just point out what these exponents are. Just concentrate, say, on the first one. So C is the open, pick a vertex. There's an open cluster. look at the volume of that open cluster. How many points are there in it? So that's a random variable. And at criticality, it decays polynomially, the tail decays polynomially, and it decays therefore as some negative power of n. And for physical reasons, the way we write that traditionally is in that form. It's just the way of doing it. So there is a critical exponent delta there. So and then there are various other exponents, and there are other exponents, arm exponents, which I haven't stated here. They're basically almost all the many of the exponents which exist at the critical point. So what we're asserting is that these exponents, if they exist for any one of these systems, so the real theorem says, let's make a statement. If rho exists for any one graph in script G, then it exists for all the other graphs in script G, and it takes the same value. Now, of course, these are not independent variables. They satisfy what's called the scaling relations, and that comes out automatically if you prove it. And this is in contrast with what we know for another old friend, an old friend of the probability community, which is this very, very special system. We take the triangular lattice, and instead of putting the randomness on the bonds, we put it on the sites. Then this lattice has special symmetries, a special symmetry, but others too, I suppose, but one very special three-way symmetry, which enables one to prove via the arguments laid out by Stasminoff and developed by others later, particularly involving calculations based upon SLE, that we can compute these critical exponents exactly, and others. So in this very, very special situation, we not only know that the exponents exist, we also know their values. But in this continuum of systems which is so close, we neither know that they exist for any one of these, and therefore we don't know their values. They exist. But of course, it must be the case that these are the values which are universal across script G. And so the problem, in some sense, the problem is to build a connection from the site model on the triangular lattice to any one model in this family of isoradial graphs. Those are bond models in the isoradial graph. We don't know how to do that. If we could do that, then we would have a true, fully universal statement. So this is only, well, one might say half of the proof, but we don't know how big a half this is. Now, quickly then, in the remaining 6 or 7 minutes, let me say how we do it. Or have 6 or 7 minutes? I'm not sure. 7, thank you. So the technique is to use the star triangle transformation. That's what that says. It says the star triangle transformation. And the star triangle transformation is well known in the physics literature as they were called Yang-Baxter, and it's been used to great reward particularly by Baxter and his co-authors in a variety of situations. We make their use very concrete in this situation, and we have to do a certain amount of technical work in order to obtain our results. But the idea is that you take a triangle. If that triangle has got edge probability as pi, and you replace that triangle by a star, and you adjust the probabilities, so A to O has got probability P1 minus P0, where P0 was the parameter here. And if in addition these P's satisfy the equation kappa is 0, where kappa is given by that formula, under those circumstances, I can change the triangle by the star, and I don't change any connection probability in the lattice. So this local change makes no difference to the macroscopic structure of the lattice. So, well known in other contexts. Now, let me just explain. This is not ancient. You certainly find it in the works of Rick Kenyon, but let me make it completely explicit. It really works neatly with respect to tracks. So I want to show you this because it's at the heart of what's going on. Imagine in this rhombic tiling you had 3 rhombi stuck together like this. Then their exterior boundary is a hexagon. So fix the hexagon, and let's switch the rhombi. There are 2 rhombic configurations of the interior which keep the hexagon. Either the edges come in at A, B, C, or they come in at the other 3 vertices. And switching from this picture to this picture just means switching from one rhombic tiling of the hexagon to the other. But when you do that, the isoradial graph changes. There's an isoradial graph outside here. There's one of the magic vertices. Instead of obtaining the triangle in this way, you obtain the star. So this is a star triangle transformation at the level of the graph. And what you notice when you do that is that the tracks also change. Here we've got 3 tracks here that you go in here, you leave there. Here you go in here and you leave at the same point. But somehow the tracks have changed here. Right? Oh, that's right. The way the tracks intersect inside here has changed. So a way of representing that in track space, if you think about what this track operation is you're taking one track and you're moving it over an intersection. So you're actually doing something dynamic in track space by moving over an intersection. And what that means is you're doing a star triangle transformation in the isoradial graph, or alternatively, you're doing a retiling of a hexagon in the rhombic tiling. And so now you ask, when we go back to the values of p, here I've got all these p's. When I do this graph transformation, the p's may get mucked up. They may get mucked up. So the question is there any particular way of allocating p's to these edges such that when you do this, actually the star triangle transformation works at the level of the percolation model? And the answer is yes, if and only if the p's were given by that formula that I wrote before. That's elementary trigonometry. So that's where that formula comes from. So once you have that, you've got a method of moving tracks around. You can move tracks around, and so and when you move a track around, you have this lovely picture, which you actually find embedded in some way, or encoded in Baxter's papers, but made explicit in our paper, which is you've got a bit of this isoradial graph here, and you introduce, you haven't got any, it's finite, and you introduce an extra edge on the left in order to make a triangle. Once you've got a triangle, you can turn it into a star. And then that creates a triangle further down the line, and you pass this triangle, it's like the beginning when you pass the parcel. This extra bit of information, this extra edge, you pass all the way down the line, and it comes out the right-hand side where you throw it away. And the effect of that is to make a sequence of star triangle transformations which interchange two tracks. So this gives you an ability to move tracks around, and as you move tracks around, you can change the local geometry of the graph. So now the game is, you start with a graph that you know about. We know quite a lot about square lattice. It has a lot of symmetry. We know about box crossings. We know RSW. So it's not something you know about. And then you move the tracks around wildly to obtain any isoradial graph in the family script G. And what you've got to show is that this box crossing property of C2 is retained as you make these transformations. And for that, you have to do some genuine estimates, you do some serious work, to make sure that these paths don't move too much, that you can understand how much the paths move. And out of that, you find that several things. One is the isoradial embedding produces critical percolation. Second thing is that within this large class, the exponents are constant, or at least some large family of exponents are constant across this family, which is a statement of universality. But it's only conditional universality because actually we don't know that they exist, but we believe they must. In contrast to the site model, where we know next to everything, but we haven't got a bridge between the bond model and the site model. So establish a connection between these things. So I haven't got time to show you my open problem, but it's in the proceedings, and I hope you'll look at it. It's a nice question for those of you who like elementary problems in probability. It's to prove that in this continuum, so this is a discrete model, where you're discrete going this way and continuous this way, and you're asking, you've got a critical situation where these are cuts in the lines, these are joins between the lines. It's to prove that in this particular model, as n, as the dimension of the square goes to infinity, the probability of a left-right crossing goes to a half. And why is that interesting? It's interesting because this is exactly the situation you get if you take a rhombic tiling. I mean, it's the square grid property, not the square grid property. Remember the rhombi are not too flat property. All the rhombi have edges, have angles bounded away from 0. So what would happen if you release that? Imagine you squashed all the rhombi. So a way of formulating that would be to say, imagine every rhombus has got an angle less than epsilon. It's nearly flat. Now you send epsilon to 0. So you take a continuum limit as epsilon goes to 0. Irrespective of the rhombic tiling, you always get this in the limit as epsilon goes to 0. So in the search for the removal of the bounded angles property, you would need to understand this question. And yet this question is, once again, one of those very simple to state questions which seems to be very elusive. By the way, if you rotate this picture through pi by 4, the answer is obvious by duality. But this is therefore, in a sense, the hardest configuration to understand. And those of you who know the area will understand what this picture means. And I leave that with you. We just point out that realizing that the epsilon goes to 0 limit gives you this particular system is an argument of myself and Ola Angel. Computer simulations around the Holroyd suggest that this number is indeed very surprisingly close to half, in the sense closer to half than you would expect for n is about 20 or 30. So thank you very much for your attention.
homogeneous case as well?
Well, a toroidal lattice is, so the way of setting that up would be to take a lattice on the, take a finite grid on the torus and pass to the limit as the size of the grid goes to 0. When all lattices
I can imagine that your track system also can be considered on the torus.
Sure.
Right? Torus.
Well, that's not the theorem, but what we're doing, I think, so it's dangerous in such august company to make rash statements, but I don't think there shouldn't be any problem going to toroidal. You're essentially going to toroidal boundary conditions. There shouldn't be any problem with that, but the track system, in the full generality of isoradial graphs, I'd want to be careful about how you do that and exactly what it means. Yeah.
Any other question or comment?
Most of your constructions can be generalized to arbitrary graphs with quadrilateral faces. For example, Merkach has defined percolation, discrete analytic functions on such graphs. Where do you use that the graphs are rhombic?
So these tracks, so I know a little bit about the work of Merkach, but I haven't read it in detail. These track systems, they have properties, they can be characterized by the properties, as the theorem of Kenyon and Schlenker, by the property that, so if you take any collection of doubly infinite lines in R2, and they have the property that no pair intersect more than once, and no line self-intersects, then that is the track system of a rhombic tiling. And we are using those properties. If you relax, so if you take a quadrangulation of the plane, which is homeomorphic to a rhombic tiling, then I guess it has a track system, but we wouldn't know, I don't think we know how to parameterize the quadrangulation. Maybe that's the answer to your question. I don't think we know how to parameterize a general quadrangulation, and therefore I think our theorems just won't be valid. I think I should read the paper of Merkach more carefully. Thank you for pointing it out. So you've got a degree of waffle, but you didn't get a full answer. Thank you for the question.
Any other question?
One of your results was that if you know the critical exponents for any one graph in the class, then you know it exists for all of them. Is that because we know also that the square lattice is isoradial, and we know the.
Yes. So if we knew, for example, you have to be a little bit careful about which exponent you need, but here's a concrete statement. If you knew that rho existed for bond percolation on the square lattice, then you would know that every exponent that I wrote up there exists for every graph in script G, and their values are universal across script G. So given a little bit of evidence, then everything else follows. But we need some input, and we don't have that input for this family of graphs. I mean, it would be, this of course is the, as it were, the next but one problem after theta PC equals 0. We know Cardy's formula for the site model on the triangular lattice. We know it for some perturbations of site model on the triangular lattice. But the obvious question is it true for the bond model on the square lattice? And so far as I can tell, unless we're having any surprises this week, nobody knows how to do that. If anybody could answer that question, then we would know that these exponents exist for all this, for this entire family of graphs. Yeah.
Any other question?
I'll just try it out in microphone. Your track system, and in particular the transformation that you're doing, lets me think about grades.
Yes.
Have you thought in that direction?
So this, what we're doing is very geometrical, it's very combinatorial. It's very elementary, it only uses basic star triangle transformations. But these ideas of tilings, tracks, general algebraic structures that tracks, algebraic properties that tracks have connections across mathematics to various other areas, including knots, braids, and other areas of pure mathematics which have resonance in mathematical physics. So we haven't thought in those directions, but we're aware of the connections. what we, the braid question is actually quite interesting in percolation. There is a percolation problem which can, I think, be reformulated in terms of a braid problem. Is Vaughan Jones here? As Vaughan explained to me how to do this, so I ought to know whether he's here or not. As not quite the classic braid problem, but a braid type problem. So I think there are methods and arguments and intuitions from a more general algebraic structure which might find application in percolation theory, but so far that hasn't been done.
Okay, let's stick on